Assalamu alaikum warahmatullahi wabarakatuh. Today we will discuss about the convolution in continuous time linear time invariant systems. Okay, so this is our topic for today. So what is LTI? LTI means the system is linear and also it is time invariant. Okay, it is also time invariant. So first of all, I will just go through the fundamental concept of linear time invariance in a brief. So let us consider we have a system. Okay, we have a system. So suppose you are giving some input as x1 of t, then the output is suppose y1 of t, and suppose if you are scaling the input by some factor a, then the output also will be scaled by the same factor a. And also if you are giving another input x2t by with a scaling factor, then you will get b times y2t. This property is called the homogeneity. That means homogeneity. Okay, then the linear system will satisfy this rule. Suppose you add this input, then the total output will be the addition of this. Suppose you add this and make a new input which is the addition of a into x1t plus b into x2t, then the total output also will be a into y1t plus b into y2t. So this property is called the superposition. So it will satisfy the superposition also. So this kind of systems are called linear time invariant system. And also our system is continuous. Okay, that means the system output is defined for all values of t. Okay, and it is not in discrete time. Okay, the system is continuous, and also the signal that we are dealing with is also continuous. So this is what going to explain. So before proceeding to the convolution, we have to prove that why we need convolution to find the output of a linear time invariant system. Suppose you have a system with the transfer characteristics t, and you are giving some input x of t and you are getting some output y of t, but how to find this output? Okay, so in order to find the output, let us consider a standard test signal. For example, I am giving to the same system, I am giving some input to the system as delta t, and I will record what is the output of the system, and I will call this output as h of t, and this is called the impulse response of the system. Okay, and what is this impulse? So this input is impulse signal, and what is this impulse signal? This is the impulse signal which is defined at time t equal to 0. Okay, and we will call it as delta t. And what is the amplitude of the impulse signal? You see that there is an arrow here. So the amplitude of the impulse signal is going to infinity, and also the width of the signal is going to 0. Suppose you take the width of the signal, it's very small width, you can see that it is going to 0. And another important part is the area under the signal. That means area, you know that it is the integration under the signal. That means integral minus infinity to infinity delta of t dt. We will get this area as 1. So how we are getting this area as 1? So before that, we should know how we are getting this impulse signal. Suppose you consider a rectangular pulse with the area. The width is delta tau and the height is delta of t, and I will call this height as I will call this height as delta 1 over delta tau. Okay, so then if you take the area, you will get the area as 1 over delta tau. Okay, so this is what the area is equal to 1 over delta tau into delta tau, and that will be equal to 1, right? So what will happen if I approximate, if I do something like this delta tau tends to 0, that means I will make it very small. Delta tau I will make it very small. Then what will happen? The signal will be having higher amplitude and a small width. You can say that this delta tau is very small, okay, and you can say that this is 1 over delta tau. So now as this delta tau tends to 0, you see that it will go as an impulse. This is delta of t, and this happens at t equal to 0, and the width delta tau as it goes to 0 and the height is 1 over delta tau will tends to infinity. But still we can say the area is nothing but the integral, so the area is equal to 1, and this is the definition of the impulse function. Now let us before proceeding with the impulse function, let us see, we will work with the approximation of the impulse function. You know that I have just shown you the impulse function can be approximated like this, with a small width and the height is 1 over delta tau, with the area is equal to 1, and this we will call as delta of t as the impulse function. So what is the area of the impulse function? It is nothing but delta t multiplied with the delta tau. So this is our impulse function. Now we have a system. I told you we know the impulse response of the system. That means I will give this input, I know what is the output. So for the impulse input, my output is h of t, and we will call it as the impulse response of the system. Now instead of using this t for representing the system, what we will do? We will use this h of t for representing the system. That means we know this response. So I can call my system with impulse response h of t, and my input is x of t and the output is y of t. Okay, so right now you see that my system is having the input x of t and output is y of t. Now if I give delta t as the input, I will get h of t as the output. That is obvious, okay, that we have already seen it. Okay, that is what the definition of the h of t. Now I am going to give some other input. Let us consider my input signal is something like this. Now for this input signal, what will be my output? This is what I am going to do. So in order to proceed how to find the output for an arbitrary input, what we can do, you see this is x of t, which is a function of time. Okay, so what we will do is we will split this signal. Let us consider this signal like this. So our signal is like this. What I will do is that I will split the signal into small pieces like this, and each piece we can say it is an impulse. Okay, which impulse? Sorry, this one. Okay, so it is an approximation of the impulse. It will become our actual impulse as delta tau tends to 0. Okay, so we will do this approximation at last. Okay, we will apply the limit like delta tau tends to 0 at the end. But right now, for understanding, let us see this is x of t and this is the function of time. Now you see, I will break down these points. You can see that this point is, let's say it is 0, then this is the point tau 1, and this is the point tau 2, and this is tau 3 and tau 4 and so on. Okay, so this is the situation. So what is the amplitude at this point? You can approximate this amplitude as x of 0, and between these 2 points, if the delta tau is very small, it will be very closer point. You can say this point is x of tau 1, then here it is like x of tau 2 and so on. Okay, so this is the situation. So now let us take the first piece. Let us take the first piece. Now what is the amplitude of the first piece? It is x of 0, and I will call the first piece as the width is equal to 0, and this is happening at t equal to 0. So the amplitude of this is x of 0. I can write it as x of 0 into delta tau. Okay, so the amplitude is x of 0, but x of 0 is nothing but x of 0 multiplied with 1, right? And what is this 1? It is nothing but x of 0. 1 is nothing but the area of the impulse function, we can say. So it is delta of t multiplied with delta tau. So this is the situation. Okay, so I hope this part is clear to you. Now if I give the impulse function to the system, I told you that if I give this impulse function to the system with the delta t and the width is delta tau, I know that my output will be h of t. But what I have to find, I have to apply the limit. Delta tau tends to 0, then only it will become actual impulse function. Okay, so here also you see that we have an impulse part, then we also have some scaling factors, and as we have seen before, you know that when I give some input x1t and I get the output y1t, then if I multiply with a some scaling factor, the output also will be get multiplied with the scaling factor because of the homogeneity property. Okay, so because of this property, so what we will do now is we are giving this input to the system. So what will happen, the system has the h of t, it will produce some output, which is, if you give this delta t, you will get the output h of t, right? Now the scaling factors are x of 0 and the another one is delta tau. So this will be the output. Now you see, I will consider the second one. Okay, this one. Okay, if I consider this one, what you will get it, the amplitude at that point, you see it is approximately, it is nothing but this is tau 1, so this is happening at tau 1, so the amplitude at that point is x of 0, but x of 0 is nothing but x of 0 into 1, but this is equal to x of 0 into what is 1? 1 is nothing but the area of the impulse function, it is nothing but delta of t minus tau 1. Why? Because it is delta t which is shifted by tau 1 unit. This is just shifted version of the impulse signal. Now this is multiplied with the delta tau. Now if I give this input, what will be my output to the system? So I will apply this input to my system in the same way that I used before. So the system, I will get, sorry, it is not x of 0, sorry for this, it is not x of 0, it is actually, this is the point of x of tau 1, because the point is tau 1. So this is equal to x of tau 1 into 1, so it will be multiplied with x of tau 1. So for this input, the output will be what? H of t minus tau 1. Why? Because the input is shifted by tau 1 unit, so the output also will be shifted by tau 1 unit, because the system is time invariant system. Now the scaling factors, you see, these are the scaling factors, so it will be x of tau 1 and also delta tau. Similarly for the next piece, so I will consider the next piece in the signal as this one, you can say this one at tau 2, you can say tau 2, then tau 3, like this. Okay, so the next piece is this one, so the amplitude is now x of x of tau 2, so I can write it as delta of t minus tau 2 in the same way, and also multiplied with delta tau. Why? Because this factor will become 1 anyway. So now you see, this is h of t, I will redraw it again. now you see the output will be shifted by h of t minus tau 2 and also scaled by a factor x of tau 2 and delta tau. So this is my output. Now you see that I can do this procedure, I can continue this procedure until I cover the whole signal. So how can I cover the whole signal? If I add the first pulse plus the second pulse plus the third pulse plus and so, you will get the complete signal, which is nothing but x of t. Then for x of t, what will be my output? You see here the output will be just addition of all the individual output for each pulse, right? So I will be getting, you see, I can write it as a summation. I can write it as a summation of all these things. That means it will be x of 0 into h of 0 into delta tau plus x of tau 1 into h of t minus tau 1 into delta tau plus x of tau 2 into h of t minus tau 2 into delta tau plus so on, right, like this. So this can be written as summation, okay, x of tau, right, x of tau n, and here you see this is tau 0. So tau 0 is equal to 0 anyway. So x of tau n into h of t minus tau n into delta tau, right? And the tau n, that means n changes from 0 to infinity. Suppose you have a piece here for the signal on the left side also, then we can have some more pieces here on the left side, right? Then what we can write, our summation will be changing from minus infinity to infinity. But we need to consider one more thing. I told you we have to apply the limit, that means delta tau tends to 0, then only it will become our actual impulse function. Okay, so we will apply the limit delta tau tends to 0. Okay, this is my output for the input, which is nothing but x of t. So I got the output, right? Now we will apply the limit. So when we apply the limit, that when I apply the limit with delta tau tends to 0, okay, what will happen here? You see that the width of the pulse will become very small, right? Then finally this will become an impulse function, right? So this summation will change. This summation, you know, it will become very close point, or we can say that it will become very continuous points. So it will be a continuous set of points. So the summation will change to integration, and the variable x of tau n will become a continuous variable x of tau. Then this will become h of t minus tau, and this one will become d tau, right? And the integration will be from minus infinity to infinity. So this will be my actual output of the system, and this is called the convolution in continuous time, linear time invariant system. So this operation is called convolution. So this is how we need convolution to find the output of a system. Okay, so this can be represented as y of t is equal to x of t convolution h of t. Okay, so this is the sign for convolution. And what is the equation? The equation is the above one. So I hope the concept of the convolution is very clear to you, right? Now let us consider how we can solve the problem, how to solve the problem. Okay, so what is given that we have to see. The h of t of a system is given, okay, and h of t, that means the input, is also given, but we need to find what is the output of the system. How to find the output? Output is x of t convolution h of t, but it can be proven that it is also same as h of t convolution x of t, right? So this can be proven. I am not going to the proof of this. Okay, so now you see this is how to find the output, but you see that in the equation for the convolution, y of t is equal to integral minus infinity to infinity x of tau into h of t minus tau d tau, right? So I can write in a slightly different way this one to understand it better. This can be written as minus tau plus t, right? And here you see this is tau, so it means that these functions, the main variables for these functions are tau. And what is here, this t, the t is showing the shifting parameter, right? Shifting parameter, which is nothing but t. Now how we can find the output of a system? So what is given here? I told you x of t is given, then h of t is also given. Okay, now we will find x of tau, then we will find h of tau. Okay, so after that, as a second step, you will change h of tau into what? H of minus tau, or we can say in general h of minus tau plus t, okay, which is the shift, okay. But in this case you can write it as h of minus tau plus t with the t equal to 0, the shift is equal to 0. So this is what we are going to find. Then the third step, what we will do, we will multiply x of tau and h of minus tau plus t, then integrate. Where we will integrate in the common region. Okay, so we will multiply and integrate. That means apply the limit in common region. Okay, otherwise other part of the function will become 0. So I will show you a problem by using this concept. Okay, so let us consider we have a system. This is our example. So let us consider we have a system h of t with impulse response. We want to find what is y of t. This is given. Then also x of t is also given. So what is x of t? I will show you. X of t is something 0 to 1, and this is x of t, and the amplitude is 1. And h of t is also given. It is another function which is from 0 to 2, and the amplitude is 1, which is h of t. Okay, so what is our first step? As I told you, the first step is to find x of tau and h of tau. Okay, so we will now find our answers. So first of all, I will find x of tau. It's very easy because this variable is t and this variable is also t. Just change the t with the tau. Okay, this now become tau. So it's become like this 1, and this is x of tau. Next, this will become h of tau. Okay, and the variable is tau. Okay, so this is h of tau. Next, what we will do, we will find h of minus tau. Okay, so h of minus tau. So I am going to find what is h of minus tau. It's very easy, just to flip it along the y-axis. So just flip it. So this 2 will goes to minus 2, amplitude will be same. Then this is h of minus tau. But I will not just simply write like h of minus tau. What I will do, I will write as h of minus tau plus t. H of minus tau plus t. So this is h of minus tau plus t. But where is this t? I didn't shift anything, but right now our t is equal to 0. Right now our t equal to 0. T equal to 0 means I will consider a pivot point on the function. So the best approximation, or the best method to consider the pivot point is, you see here, this is our pivot point. I didn't shift anything, so I will consider here this 0 as my pivot point. Okay, so now you see this is showing that t equal to 0. So this is the point of my shift. Okay, so since this is t equal to 0, it means that this point is nothing but t minus 2. So my function right now, it will become, I have something here t, and this point is t minus 2, amplitude is 1, and this is the function h of minus tau plus t. But right now our t equal to 0. Okay, so this is a function in tau. This is a function in tau, and t is the shifting parameter. Next step is what? Just multiply, and then you have to integrate. So let us see. So before multiplication, I will show you how we can. I will just redraw the functions again. So this is our x of tau, okay, multiplied with what? Our function, which is here, right? So you see the shift parameter, this is t and this is t minus 2, but the shift parameter, we need to consider all the possible values of time for the shift. Okay, so for shift parameter, which is nothing but t, we will consider t changes between minus infinity and infinity. That means we need to consider all the possible values of time. So what we will do is, we will start with the lower values right now. So for t less than or equal to 0, we can say. So if t is less than 0, okay, for t is less than 0, what is the situation? So if t is less than 0, you see the shift will be a little bit somewhere here. If t is less than 0, the function will be here, right? So this is point is t, and t is less than 0, and this is t minus 2, and the amplitude is 1. Right now you see the function has the value on the left side, x of tau has nothing, and this is the function h of minus tau plus t, right? So here there is some values, but here nothing, and here nothing. So if I multiply, you see y of t is integrate, multiply and integrate. You see 0 multiplied with something, 0 multiplied with 1 or whatever, 1 or 0. So it will become the answer as 0. So for t less than 0, y of t is equal to 0. For t less than or we can say up to 0, this is a situation, right? So for t less than or equal to 0. So this is the output. So I hope this is clear to you. So we got for t less than 0. Now you see the function, what we have flipped, actually we are going to move it right. We are going to move it right. That means we will make it for t greater than 0, t greater than 0. So you see here, this is our 0. So now t is greater than 0, and this point is t minus 2, and here it is the tau, where variable is tau. Now you see, if you multiply, now you see this is 1 and this is 0. If you multiply, your t is here in between, okay, your t is here. As you compare with this one, your t is somewhere here, okay. So now when you multiply, you see that on the right side of this t there is no function, and here there is something, but on the left side of x of tau there is nothing, so the common region for the integration will be this much, right? So y of t will be equal to the amplitude here, it is 1, so x of tau is 1 multiplied with the amplitude here is also 1, so 1 multiplied with 1 d tau and the integration, and the integration limit changes from 0 to t, 0 to t, so this will become tau and apply the limit 0 to t, so this will become t minus 0, which is equal to t. So y of t is equal to t for what? T greater than 0. But as you see this, you know that this is our x of tau, and right now our h of tau is here, sorry, h of minus tau plus t with t greater than 0, it is somewhere here. Suppose if I move it further, what will happen? It will cross this point, it will cross this point. If it cross that point, then what will happen? I will write it, it will be here, right? So there is nothing for x of tau, right? There is no value for x of tau for t greater than 1, but there is something here, so if I multiply, the answer will be 0, so my integration limit will change from 0 to 1 anyway. So this is the situation. So my output, what I have shown here, it is valid until the t reaches 1. That means this output is valid only for, and we can say that it will be also for, and t less than or equal to 1. So if t is greater than 1, everything will change. So it means that t is greater than 0 and less than 1. So this output is valid for t greater than 0 and less than 1. It means that the t is between 0 and 1. So this is my output. So next I will consider this case. Okay. So for considering that case, I will redraw both x of tau and h of tau. Okay. So let us consider, not example, sorry for this. So let us consider the situation for t greater than equal to, we can say, greater than 1. Okay, so in this case I will first draw x of tau. This is x of tau, and this is 0 and 1, and this is tau. Okay, now you see I am having h of tau, h of minus tau plus t, but t is greater than 1, but t is greater than 1. So here it is your 1, the point, and I will mark here t. So t is greater than 1, and this is my situation. So this is t minus 2. So in this case, if I multiply these two signals, you see that the common area is nothing but this much, right? So my y of t will be equal to, this is amplitude as 1, this amplitude is also 1, so 1 into 1, right? Then d tau, integration will start from 0 and it will end at 1, so from 0 to 1. So this will become tau and integrate from 0 to 1. That means the output y of t is equal to 1 for t greater than 1. But don't stop here. What will happen if t goes further? So suppose it moves here. If this point moves further, finally you see you will end up something like this. This is t and t minus 2. The problem is, now the integration limit is not from between 0 and 1. The common area has changed, the common area has decreased, right? So the common area is not same as previous. So in such a situation, what we have to do, we have to recalculate it further. So our situation is valid until the point, this is t and this is t minus 2. When t minus 2 reaches 0, no issues, but when t minus 2 crosses 0, everything will change. So what we can say, that our t minus 2 should be less than or equal to 0, or we can say t is less than or equal to 2. So in this case, we have t greater than 1 and t minus 2 less than or equal to 0, or we can say that t is less than or equal to 2. So this is our conditions. This is our condition. That means t is greater than 1 and t is greater than 1 and t is less than or equal to 2. That means t is less than or equal to 2 and greater than 1. So this is the output. That means t is between 1 and 2. Now let us proceed to the next situation. That means when t minus 2 crosses, suppose this t minus 2, now it is at 0, suppose it crosses 0, that means for t minus 2 is greater than 0, sorry, greater than 0, or we can say that t is greater than 2. Both are same, right? So this is the situation when t is greater than 2, because from this equation you will get t is greater than 2. So what will happen here? I will draw first x of tau just for the convenience, then this is tau, then I have my h of tau. Now you see our point has crossed here, so this is my t and t minus 2. Now you see our t minus 2, this t minus 2 is greater than 0. This is 0 here, okay, and this is the point t minus 2 and the amplitude is 1. Now you see the integration limit is not same as previous. The integration limit is this much only. This is the common region. So you have to multiply here 1 and this is also 1. So y of t is equal to 1 into 1 d tau. Integration limit is changing from t minus 2 to 1, right? That is the common region. So this will become tau and become 1 and t minus 2. So this, y of t actually we will be getting as 1 minus t minus 2. So which is nothing but 1 minus t minus 2. I have to put a bracket here. Now you see it is nothing but 3 minus t. So this is my output. But this output, you see y of t which is equal to 3 minus t is valid until the point this t minus 2 reaches 1. That means our t minus 2 should be less than or equal to 1, which implies t is less than or equal to 3. So this is happening between t greater than 2 and less than 3. It means that t is less than or equal to 3 and greater than 2 between 2 and 3. So this is my output. Next is the situation is for t when t minus 2, that means this point crosses 1. When t minus 2 is greater than 1, it implies t is greater than 3. So what will happen if t is greater than 3? If t is greater than 3, you will see that the function has moved here. That means t minus 2, this is t minus 2, and here t minus 2 is greater than 1. Okay, so in such a situation you see it has crossed here and there is no signal for x of tau in this region, and there is signal here for h of t minus tau, and if you multiply the answer, obviously the answer will be equal to 0. So y of t will be equal to 0 for t greater than 3. So this is our output. So now how we can sketch this output. Before that I will show you complete output. This is our time and y of t. Okay, so we have seen the first one. I think it's here, right? Yeah. So y of t is equal to 0 for t less than 0, and y of t between 0 and 1, it is nothing but t. So for t less than 0, output is equal to 0. When t is between 0 and 1, the output is t. Okay, then what it is? Yeah, between 1 and 2, the output is 1. So the output is 1 between 1 and 2. And now you see between 2 and 3, the output is 3 minus t. So the output is 3 minus t between 2 and 3, and for t greater than 3, the output is equal to 0. So how to sketch this? It's very easy to sketch. Just observe the output is a function of time. Okay. Now you see what are the points here. If you see the points, here 0, then 1, then 2, then 3, and here also 2 is already repeated, no issues. So 0, 1, 2, then 3. Okay, this is our output y of t. Now how to sketch it? Now for t less than 0, that means this portion, the output is equal to 0. Output equal to 0. When between 0 and 1, the output is nothing but t. So I will put first t equal to, so this is my output. So I have the values between, the t is between 0 and 1. When I put t equal to 0, the output is 0. When I put t equal to 1, the upper limit, the output will be equal to 1. So it is a straight line, it is very clear. Then between 1 and 2, the output is 1, it is a constant, right? When between 2 and 3, how to calculate? Just put t equal to 2. When putting t equal to 2 here, this will become 3 minus 2, the answer will be 1. So you will reach here 1. Then when you put t equal to 3, that means 3 minus 3 will become 0. So this will become 0. So this is a straight line again. Then for t greater than 3, the answer is 0. So this is our output. Okay, so I hope this problem is very clear to you. Okay, so we will see another example anyway. So I have a system with impulse response as h of t, and the output is y of t. Okay, now my input is x of t. The input is given, it is something like a function like this. So this is going to 2, and this is 1, and this is our graph. Okay, this is the function of time, and our h of t is also given. It is a simple function, it's 0 to 1, and the amplitude is 1. But first of all, we need to find what is the equation for this line. We have no idea, right? So how to find the equation of this line? So we have to see the what is the in xy plane. In xy plane, equation of the straight line is x minus x1 by x2 minus x1 is equal to y minus y1 by y2 minus y1 in xy plane. So what is this point? This point is 0 comma 0, and this point is, you see, 1 comma 2. So you can say this is your x, this one is as x1 y1, and this as x2 y2, if you consider this. So this is your signal x of t now, right? So so this is the situation. So you can get the equation as x minus x1 is 0 divided by x2 minus x1 is 1 minus 0 is equal to y minus y1 is 0 divided by y2 minus y1 is 2 minus 0, right? So this will give you y equal to 2x, but instead of y we have x of t, and instead of x actually we have t. So sorry for this, something happened. Yeah, so instead of that x we have t, instead of y we have 2t. So now instead of y we have t, so the equation is 2 times t. So this is our equation. Now why as a first step I told you, what is our first step? You need to find what is x of tau and you need to find what is h of tau. H of tau is very easy, this is a function of time, so just find as a function of tau, this is 1 and 0 and 1. But x of tau also very easy, this is a function of time, the same graph, this going to, this is going to 2, okay, and the equation is 2 times tau, not t, okay. So be careful, because this is a function of time, now it is a function of tau. So this is our first situation. Next what we will do, we will find what is h of minus tau plus t, but our shift we will put it as 0. That means it is nothing but h of minus tau. H of minus tau is very easy to find, just do the time reversal, flip it along the y-axis. So this is tau, this minus 1, and here it is h of minus tau plus t, but our t shift is equal to 0. Now we have to mark the point for shift. I will mark the point again here at the same like the previous problem, always do like that, and this is the point t, and our shift t is equal to 0. Since this is t and the overall distance is, you see, minus 1, so what I can say, this is t minus 1, t minus 1. So I am going to rewrite it again. This will be something like this, okay, minus 1, t minus 1, and this point you can say this point is t, and this is your h of minus tau plus t, okay, but here the shift t equal to 0, okay. So this is the situation. So you got two main functions, you know, this one you got it, and also this one you got it. Now you just need to multiply and integrate as discussed in the previous problems. So you see here, I will just draw x of tau, this as amplitude 2, and so this is x of tau, okay. Now we are going to find the output 4, anyway I will mention it, and you see I will put our t less than 0, okay. So if I put our t less than 0, the function will be here, this is t and t minus 1, and right now t is less than 0, right, amplitude is 1, so for t less than 0, or we can say t less than or equal to 0, up to 0, this is the situation, okay. Now you see, for this function there is no value for the first function, and here there is some value, so if you multiply this, output will be equal to 0, because there is nothing common, right, there is no common region, so the output will be equal to 0 for t less than or equal to 0. So this is the situation. Next I will consider the situation with t greater than 0, okay. I will draw our x of tau, sorry for this, I will draw our x of tau also, just for the convenience, okay, and this is 2, and this is 1, here 0, and this is a function of tau. Next, for t greater than 0, that means I am shifting the function further, so it will be here, for example. So this is our t, and t is greater than 0, this is our 0, and this is t minus 1. Now you see, if you multiply, this is 1 and here it is 2 tau, the common region is different, the common region is up to this region, okay. So our integration limit for y of t will be between 0 and t only, so 0 to t, and the first function amplitude is 2 times tau multiplied with the second function amplitude is 1, then d tau. So if you integrate, you will get this as 2 times tau square by 2, which become tau square. So the answer is tau square. Then you have to put the limit this become t square. Okay, so y of t will be equal to t square for what? T is greater than 0. But be careful, now you see, if I move it further, what will happen? It will cross 1. It will cross 1. If it cross 1, then what will happen? The function, if it is crossing 1, that means if t is greater than 1, then the region of the integration will change. The region of the integration will change. So this is valid for t greater than 0 and t is less than or equal to 1. Up to 1 there is no issue. That means the t is between 0 and 1. T is between 0 and 1. So this is the situation. Now let us consider this other case anyway. That means for t is greater than 1. So for t is greater than 1, what is the output? Now you see, I will draw the x of t for convenience. This is tau, this is 2. I will draw x of tau also. This is our tau. Next we have our h of tau, which is shifted further, so it is here. So the function will be like this. So this is our t and this is t minus 1, and you know here it is our 1. So here you see t is greater than 1, right? So t is greater than 1. Now our region of integration, you see the region of integration will be this much, okay, up to this region. So y of t will have the region for integration, so t minus 1 to 1, and the output is 2 times tau into 1 then d tau. Okay, so you will get the integration again tau square, but the limit is from t minus 1 to 1, which become 1 minus t minus 1 the square. Okay, but this output will not continue up to infinity, because you see, suppose this suppose the point 1, suppose the signal crosses the point 1, that means the point which is t minus 1 is greater than 1, then we can say that t is greater than 2. If this is the situation, then the output will goes to 0, because there is no signal for t greater than 1 for x of 2 tau, sorry, x of tau. So this will be continuous, this will be continued until t minus 1 is less than 1, or we can say that t is less than or equal to 2, or we can say less than or equal to. So y of t, we can say that the output y of t will be equal to 1 minus t minus 1 the square for t is greater than 1 and less than 2, that means t is between 1 and 2. So this is our output. So I think this is clear. Now it is obvious that for t greater than 2, what will happen? You see, as I mentioned here, the output y of t will be equal to 0. So for t greater than 2, so this is our output. Now right now I am just going to sketch the output. So this is t, then we have y of t. So we will just go through all these things. So the first one is for t less than 0, y of t is equal to 0. So for t less than or equal to 0, y of t is equal to 0. Next is when t is between 0 and 1, it is t square. So t square for t between 0 and 1. Then between 1 and 2, it is 1 minus t minus 1 the whole square, right, which is between 1 and 2. Okay, so between 1 and 2, then it is equal to 0 for t greater than 2. So how to sketch this? It's very easy. So you see what are the points here. Here we are 0 0 1 1 1 2. So that is 0 1 and 2 only. These are the points, right? So this is our y of t. Now y of t is equal to 0 for t less than 0. So everything is 0 for t less than 0. Then it is t square So how to plot t square? T square is a curved graph, you know. So when just put t square is equal to t is equal to 0, so it will become 0 square, it will become 0. So this is the value. Now at 1 just put t square, means it is nothing but 1 square, right? So 1 square is also 1, and the graph is a curved graph because t square is the equation of the parabola. Now you see between 1 and 2 it is 1 minus t square, so it is also a curved graph, but you see that it is 1 minus t square, that means it will be a decreasing graph. Now just put here t equal to 1, so it will become 1 minus 1 minus 1 square, the answer is 1. So the answer is again 1 only. Now for t is equal to 2, that means the upper limit, what is that? 1 minus 2 minus 1 the whole square, which is nothing but 0. So it will be going to 0, and the graph is a curved graph, so it will be something like this. Okay, next is for t greater than 2, the answer is 0. So this is t square, this is 1 minus t minus 1 the square, here it is 0, here it is 0. So this is our output y of t, which is a function of time. So I think you understood how to do the problems. Let me show you a few cases, like we have x of t something like this, and sorry for this, we have x of t has a graph something which is very simple, and h of t, you know, suppose h of t is something like this. Okay, now you see that the more simple one, the simple one is actually x of t. So usually prefer the simple one for shifting and for flipping. Okay, you have to first time reversal, that means for flipping and moving. So what we will do, you know that we have to perform actually x of t convolution h of t. Instead of doing this task, we will perform h of t convolution x of t, and you will get the same answer. So what I will do is that I will consider the first signal as h of t instead of x of t in this situation. Okay, so what I will do is that I will consider my first signal like this. Okay, the first signal as this one, that h of t. Then I will find what is h of tau. So you will get the graph like this, which is a function of tau, and this is a function of t. And then we will consider our x of t. Then we will find what is x of minus tau. As I told you before, x of tau you find it, then x of minus tau, then you will, this is flipped, then try to move, right? So mark the t here. Okay, so this is how to proceed. So try to move the simple signal instead of the complicated one. So another case, actually what I want to tell you is that suppose you have x of t something like this. Let's see, this is a graph. Okay, and h of t something which is having on the negative side and the positive side, it is minus 1, and here it is 2. What you have to, you know how to find x of tau, it is very easy. Okay, but I will find what is h of tau. How to do it? Just replace the t with the tau. So this is the graph. Okay, sorry. So this is the graph, minus 1, 2, and here it is 0. Then you find what is h of minus tau. How to do it? Just simple. Okay, I will show in the next line. So what I will do is I will just flip it. So this will become minus 2 and 1. This is h of minus tau plus t, I will say, but t, the shift is equal to 0. But where to mark your t? This is very, very important. As I told you in the previous problem, just mark the t here. Okay, don't be confused. Just mark the t here. Since this is t, and I told you that the shift is equal to 0 right now. The shift is equal to 0 here, as I told you. this is t, then this point is 1 unit ahead of this t. So we can say that this point is t plus 1 and this point is t minus 2. Okay, so this is how to mark the point. When you do the integration, you can start actually in this problem like this. I will show you. Okay, so let us consider how we can do this integration. You know, first I will just write this function. This is, let's say this is 1 and x of tau. Then you see I have the function something like this, right? This is at 1, that means t plus 1, and here it is t minus 2. Now you see there is already an overlapping, so move the function first, because we want to change our t from minus infinity to infinity. But here right now the point, this is your t, that is equal to 0 right now. This is h of minus tau plus t with t equal to 0. And now what we have to do, we have to shift this back a little bit so that there is no overlap, and we have to find that limit. So how? Let us shift this point, as I told you, let us shift this point just below 0. Then what will happen? You see, this will be the situation that t plus 1, and here it is t minus 2. Now this is your 0. So what is the situation? T plus 1 is less than 0, or we can say that t is less than minus 1. So now you got the limit actually. Now if you multiply this 2, if you multiply the output y of t is equal to 0 for t less than minus 1. So this is the situation, and this is how to proceed. If you want more examples, just tell me. Inshallah, I will make another video related to this kind of example. Thank you.